What's up, everybody? Welcome back. We're going to get started on a new fluid mechanics problem today. Today we're going to be talking about flow through non-circular pipes. And the first thing I want to work on today is looking at this. We make an important approximation when we talk about non-circular pipes. And that's what we're going to do first. So explain the primary approximation used to calculate frictional heating in non-circular pipes. So I'm going to tell you right off the bat, the approximation used is that the shear stress in a circular pipe is approximately equal to the shear stress of the fluid in a non-circular pipe. That is the approximation. But let's talk about how we get there and what that means in context. So if you remember, for a cylindrical pipe, we know that the change in pressure across that pipe times the area, cross-sectional area of that pipe, is equal to the shear stress, again of a circular pipe, times the area in which the fluid contacts the surface, which is going to be the surface area, the inside surface area of the pipe. So we have something like the circumference times the length, right? So 2 pi r times the length. Okay. And then for we can do the same thing for, let's say, like a non-circular pipe, right? So just like before, we have the change in pressure on a non-circular pipe, this is a circular pipe, times the cross-sectional area is equal to the shear stress of the non-circular pipe times the, again, the surface area is going to be the perimeter, just like the circular pipe times the length, except the perimeter is not 2 pi r, right? It's the 2 times the width plus 2 times the height. I'm just going to keep this term as the perimeter times the length. Okay, and you'll see what I'm doing here in just a second. So if we move forward with these expressions, let's see what we get. So we have delta P times C. What's the area of this pipe? The cross-sectional area is pi d squared over 4 is equal to the shear stress times 2 pi. I'm going to change this r to diameter, so diameter over 2 times L. Okay, we can simplify this. Pi cancels out, d squared, d 2. Looks like we're left with delta P. That circular pipe is equal to, we'll just do it in 2 steps here, why not? Okay. Delta P circular is equal to, move this to the other side, we get tau C L 4 over d. Okay, and let's go ahead and solve for, I guess I should have just done this the other way. Let's just go ahead and solve for that shear stress. So we have the shear stress in the circular pipe is equal to delta P times, delta P of the circular pipe times the diameter over 4 times the length. Okay, and that's the expression we get for the shear stress of a circular pipe. Now, let's go ahead and look at this one, do the same operations to it. So, delta P, the non-circular pipe, is going to be equal to the shear stress in the non-circular pipe times the perimeter over the area times the length. Now, for non-circular pipes, we have created a variable called hydraulic radius. Okay, and hydraulic radius, we'll denote by HR, is equal to the area over the perimeter for a non-circular pipe. So you can see here we have the inverse of the hydraulic radius in our expression. 1 over HR. So if we substitute that in there, we get delta P for the non-circular pipe is equal to the shear stress in the non-circular pipe times 1 over the hydraulic radius times length of the pipe. Again, solving for the shear stress, we get delta P okay. Oh, great. I think so. Divide, yep. Okay. And the approximation that we make is that these are equal. Now, here's the consequence of this. So, you might remember that in the Bernoulli's equation for this like horizontal pipe where there's no change in kinetic energy of the fluid inside it, meaning it's the same, in this case it would be like the same diameter all the way across, in this case the same width and height all the way across. We can write the expression delta P over rho is equal to the negative, or the frictional heating there, right? Okay, and what we can do is we can take this expression back up one step, okay, and we can divide both sides by rho, and then it should equal the frictional heating for a non-circular pipe. So let's go ahead and do that. I'm going to back this up one step, so we don't actually need this here. Keep that there. And remember, the approximation is that this is equal to this. That is the approximation. Okay, so if we divide both sides by rho, I'm going to write that as a note here, divide both sides by rho, we get the following. Delta P non-circular over rho is equal to, now here's where the approximation comes in. We can go ahead and plug this guy into here. Delta P circular times the diameter over 4L. Remember, we divided this side by rho times 1 over the hydraulic radius times L. And this also equals the frictional heating for our non-circular pipe. Okay, recall that the frictional heating for our pipe, frictional heating, we did this in a last video, or in a previous video, is equal to 4 times the fanning friction factor times L over D times V squared over 2. Okay, and this is equal to pressure, the change in pressure, excuse me, for a circular pipe over rho, which is exactly what we have right here. Okay, so we can go ahead and we can plug that into here. We get this expression here times D over 4L times 1 over the hydraulic radius times L. Okay, we can do some algebraic things here. L's cancel out, diameter cancels out, 4 cancels out, and I think we're left with here delta P circular over rho is equal to the fanning friction factor times L V squared over 2 times the hydraulic radius. Okay? And this would express the frictional heating for our non-circular pipe. Okay, so this is the approximation we make here, that these shear stresses are the same, and we can do these algebraic manipulations to come up with this, this equation. I want to make a quick edit here. We just finished up filming, but I realized that when I wrote this down, I forgot to carry in the negative sign in. So when we derived this expression previously, this was a negative and a negative. Okay? So these would carry through. We would get this into here, so on and so forth, and we get a negative sign there. Okay? That's all. Okay, so if you remember from just a second ago, we just derived this expression for the frictional heating inside a rough, non-circular vessel. Okay, and now we're going to try and apply this expression that we just came up with in a sample problem. So, these are the conditions we're being given. We have an open rectangular channel with a cross-section 4 meters wide. It is delivering 20 cubic meters per second of water, okay? And it's sloped at 5 degrees and has a surface roughness variation of 5 millimeters. And we want to know how high is the water in the channel. So just to give a quick drawing of what our channel might look like, we have, here's our horizontal reference, and then maybe here's the side of our channel at 5 degrees. And we have some width to our channel that is 4 meters. Okay, I'm just going to do my best here to draw. And we have water flowing down this. Channel. Okay, and it's flowing downhill. Okay. So, what we need to do is we're going to use a variation of the Colbert-White equation combined with the Bernoulli's equation expression to solve this problem. So the first thing that we can do here is kind of define our variables on the problem. So we have the length of flow, that's L. We also have some difference in height here, you can see. And this is important. The reason this is important is because in our Bernoulli's equation right now, we're only accounting for a change in pressure as the change, the only thing that's changing the energy of the system, right? And that's not entirely true here. Actually, the pressure isn't changing off from one end to the other. It's atmospheric pressure at both ends. What is changing here is the height. So we have a change in potential energy of the system rather than any sort of work-related energy or kinetic energy. We have a change in potential energy. So really, the correction we can make to our expression here is as follows. The potential energy is now included here, and this equals our expression we solved for to the right already. Okay. And we just explained that this is equal to 0. We have no change in pressure from one end to the other. It's atmospheric pressure. It's an open air channel, open rectangular channel. Okay. So let's go ahead and start plugging some terms into these variables. What we want to do to be able to solve this, we're going to set this equal to 0 and then minimize it. So we have, I'm going to rewrite it down here. 0 equals G delta Z. We'll do plus F L V squared over 2 times the hydraulic radius. Okay. So we know G's acceleration due to gravity. what is delta z here in terms of variables we understand? Well, delta z is going to be the length times the sine of our angle theta, right? So we can already start to rewrite this. 0 equals g times L sine theta plus our friction factor. We know L. Velocity. What is the velocity? Well, the velocity can be calculated through the flow rate, right? We know that the flow is equal to the velocity times the area. Okay. Therefore, the velocity is equal to the flow over the area. The area, the cross-sectional area of our culvert here, or ditch, or whatever you want to call it, is the height times the width. Okay, so I'm just going to write h times w. Okay, and then we have velocity squared. So let's go ahead and put that in here. Q over h times w squared. Okay, divided by 2 times the hydraulic radius. Well, what is the hydraulic radius? If you remember, the hydraulic radius is equal to the area over the perimeter. Okay, so the area is going to be, again, the height times the width, and the perimeter is 2 times the height plus the width, right? Yeah. Okay, so we can put that back in here. We get HW over 2H W. Okay. Okay, what else can we do with this? Okay, so actually, I made a quick mistake here. The perimeter is, it is the perimeter, but really it's the area, or it's the length of contact perimeter. So in this case, the walls of our culvert, I guess you can imagine, kind of sit like this. It's open air, right? So there's contact along here and along the bottom and along the other side, but not the top. So we should fix this. It's really only 2 times the height plus 1 times the width. Okay, so that looks a little bit better there. Okay. Good. Let's go ahead and try and simplify this. Do some algebraic manipulation. Okay, so we have L Q squared, and then we have divided by 2, this HW squared down here, times H times W over 2H plus W. And rewrite, keep going down here, G L sine theta plus F L Q squared over, we have now, I'm going to move this back up to the top, so we have 2H plus W up here, and on the bottom we have what would appear to be 2H cubed W cubed. Okay, we can divide both sides by L. L comes out. We're left with 0 equals G times the sine of theta is F Q squared 2H plus W divided by 2H cubed W cubed. Okay, that appears to be right. This is going to be the result of our first equation. This is the Bernoulli's equation with all the variables that we have given, plugged in. The second equation that we're going to use because remember we're solving for how high the water is. And the things that we don't know in this, we know G, we know theta, we know W, we don't know H, that's what we're trying to solve for. We know Q, and F is a function of the Reynolds number and the roughness, right? We know the roughness, but we don't necessarily know everything about the Reynolds number. So our second equation is going to be a modified version of the Colbert-White equation, which I will join you on the computer for here in just a second. We're going to use both of these equations. We're going to set them both equal to 0 and then optimize them. All right, so join me here on the computer and we'll keep this going. All right, what's up, everybody? I think I've got you here in front of me and then off to the side as well. You can see we've got up on the board the problem we just solved. We haven't solved it yet. We're going to keep going on it. So we've derived this expression here from the Bernoulli's equation, and we set it equal to 0. And now we're going to use an additional equation to solve for the height of the water. Okay, so what is this Colbert-White equation that we're going to be using? Well, I've gone ahead and Googled this. Let me share my screen with you as well so you can see this. Let's go ahead and share screen. Okay. And I've got here, this is the, let's see, the Colbert-White equation. Expresses the Darcy friction factor as a function of Reynolds number, blah, blah, blah. And then we have the free surface flow. This is the one we're interested in. Okay. So we're going to be using this expression here. And we're going to set this one equal to 0 as well. We're going to algebraically manipulate it to 0, and then we'll have two expressions that equal 0 with our two unknowns, okay? And our two unknowns, just as a reminder, are the height and then the friction factor F. Okay, so with that in mind, I'm going to pull up our handy Excel, and we're going to try put all of our variables in here. So let's go ahead and name some of our variables off. I'm just looking at the equation we have on the board, and right off the bat, I see we have G. We're going to need to define that. We have theta. We'll need to define that. We have Q. We know Q. We have the width. We have epsilon for our roughness there. We'll also need the hydraulic radius, right? That's with the hydraulic radius. We will need, what else do we have in here? The Reynolds number. Okay. We need velocity possibly. We might need, oh yeah, 'cause the Reynolds numbers depend on velocity. And I'm sure I'm forgetting one, but we'll come across it eventually. And then we're solving for, remember, H, and we don't know F either. That frictional heating factor. Okay, so G we said was 9. We know is 9.81. Theta we said is 5 degrees, but we should probably put that in radians. So let's go ahead and say 5 times pi over 180. Yes. Okay. We know that Q is 20 meters cubed per second. We know the width of our culvert is 4 meters. Epsilon is 5 millimeters, so that's 5 times 10 to the minus 3. Okay. We have the hydraulic radius HR. Do I want to put that one in yet? I'm going to skip that one for now because we can come back and name that afterwards.
We have the Reynolds number, velocity. I know I'm missing something. Oh, we need the viscosity and density of water. Let's give us some more room for those. So we have rho, we have mu. The density of water is 1,000 kilograms per meter cubed. The viscosity of water is 10 to the minus 3 Pascal seconds. Okay. We have height. We have the frictional factor F. Okay. Let's go ahead. Let's try and do our velocity here. So velocity. Let's see. What would? Yes. So if you look back up on our board, we have the expression for velocity there is Q over H times W. It's Q. Oh, you know what? And as I'm doing this, I'm naming all of these. Okay. So come back to that in just a minute. Where's those at? You can name these there. Create name. Okay. That will allow us to refer to these. So velocity is equal to Q divided by H times W. Surprised that's working since it doesn't know what H is yet. I didn't actually define H. And now it's not going to work yet. We'll have to, and eventually we'll have to make a initial guess for these. So I'm just going to put like 1 meter in here and 0.05 or something like that in. Okay. Okay, so we've supplied some initial guesses there, and then it's calculating the velocity now. We know the Reynolds number is equal to rho v d over mu. Is that correct? Think about that. Oh. Rho. D. What are we going to do about D? We don't know D. I'll think of that in a second. We have the hydraulic radius. We said the hydraulic radius was equal to the area over the perimeter, which is H times W divided by 2H plus W. You can put that one in. That's pretty simple. We have H times W divided by 2 times H plus W. Forgot my periods there. Okay. That's right. So if you, I'm not sure if I said this. So the hydraulic radius happens to be equal to half the radius of a cylindrical pipe, or 1/4 of the diameter. So that's how we can get the Reynolds number here. We have rho times V times, and then instead of D, we just have 4 times the hydraulic radius divided by mu. Okay. And then I'm sure I'm forgetting something, but that seems to be all the things that I can remember right now. Let's go ahead and type in our 2 equations. So we have 2 equations. We have Bernoulli's equation, and then we have the Colebrook-White equation. Okay. And the Bernoulli equation is the one we just solved for on the board. And remember, we're setting this equal to 0. So let's go ahead and type this in. This is a little bit meticulous, but I think we can get it. We have g times the sine of theta. Okay, plus the frictional heating factor, friction factor times, oh, this is a big one here. We got, okay, q squared no, just don't trust the order of operations. So we have q squared on the top times, what else is on the top? We have 2 times h plus w. Okay. Divided by make sure I got our parentheses in the right spot here. I think that's good. Yeah, I think that's in the right spot. Okay, divided by 2 times, we have h cubed and w cubed. Okay, let's see what that gives us. Theta q squared times 2. Ah, okay, I just found a mistake that we made. So if you look at the board, you'll remember that we took g delta z as g L sine theta. However, delta z is equal to the final height minus the initial height, which really is going to be a negative number. So that quantity needs to be negative in here. So we can go ahead and change this to negative. Okay, I think we can move forward now. So the Colebrook equation, now we can kind of insert this. If we set this equal to 0, it's the same as taking this term here and adding it over to the other side, right? So let's go ahead and type that in here. We have 1 divided by the friction factor, square root of it, right? Plus, I'm adding it to the other side. 2, this is gonna be a long one. 2 times the log of, let's do our first fraction there is the epsilon value divided by 12 times, oh, not the Reynolds number, the hydraulic radius. Okay, plus 2.51 divided by the Reynolds number times friction factor to the 0.5 power. Where are we with our parentheses here? I need one for the log, one for the multiplication. Okay. And then we will get negative 1.92. Okay. Now, obviously these aren't the correct guesses for height and friction factor. If they were, these would be 0, right? So what we can do is we can do a sum of squares error to optimize these two equations. So if we take this and we say this is equal to this guy squared, Okay, remember these should both equal 0 ideally. And obviously 0 squared should equal 0. And 0 plus 0 should equal 0. Then we can square both of them, add them together, put that in this cell here. This will be our check cell, or something like that. This is equal to the sum of these two guys. Okay, and this is the cell that we want to reach 0 in. Okay, so we can go ahead and use the solver for this. If I don't need that anymore, open this back up. Where's our solver at? I think it's in data. Yep, solver. Okay, we want to minimize the value of G4, okay, by changing the cells for height and friction factor. Okay. Our unconstrained variables are non-negative. We're using the GRG nonlinear solving method. And just make sure our automatic scaling is checked. Okay, and let's hit solve. Okay, and there's our solution. So you can see we get a very, very small number. Effectively, it's basically 0, right? And we have this output for height. So this is our height in meters of the water, 0.805. All right, so that's the end of this problem, but we are going to keep chugging along. I'm going to have you meet me back on the whiteboard off this meeting for the last part of this problem.
Okay, last part of what we're going to do today. So we're going to talk about optimizing the cost of pipe diameters, or optimizing pipe diameter to optimize cost, right? So we want to derive an expression for the optimal pipe diameter when we have an annualized capital cost, some coefficient, right, times the diameter of the pipe and length of the pipe. And then in addition to that, we have some annualized pump related like power costs, right? So we have the power cost rate times the amount of power we use. Okay, so this makes sense. And our total annual cost are going to be these two things added together. Okay, so let's figure out how we can optimize this cost. Well, we can remember our Bernoulli's equation that we've been writing. We have this change in pressure over rho plus G delta Z is equal to friction factor, or excuse me, frictional heating. All right, and now if we have just a flat pipe per se, right? Like let's say we have a pipe laying on the ground like this, and we want to get water from one end to the other. Well, with no pressure difference and no potential energy difference, we're not going to be able to move that water without a pump. Okay, so say we have a pump right here that moves the water from one end of the pipe to the other. And this is what generates our pump cost, right? Our power cost. Okay, and so if you remember, previously this wasn't all we had ever written for this equation. We'd always assumed that we're not doing any non-flow related work. Well, now we're doing non-flow related work. This is work caused by a pump. So we have to add to this expression our non-flow related work piece there, right? So in this expression, we know that this is 0 and this is 0. So really all the work that's being put in by the pump is just counteracting the frictional heating, right? And so we get this expression, non-flow work is equal and opposite to frictional heating, which we already said was equal to 4 times the fanning friction factor times we have L over D V squared over 2, right? Okay, so keep that in mind, and let's talk about power for a second. So power, if you remember, is energy, work-related energy, which is usually expressed in joules per unit time, which is usually in seconds, okay? And what we have here is joules, like work, right, per mass. Okay, so what we can do to get power out of this, we can say power is equal to our non-flow work per unit mass times mass per times flow of mass, right? Okay, so what we can do is multiply both sides of this equation by this mass flow factor. Okay, so now we get dWNF dm times dm dt. I'm going to rewrite that now as just dw dt, okay, or power, not to be confused with pressure. Power is equal to 4F L over D, V squared over 2 times our dm dt. I'm going to shorten that just to make this algebra easier and just call it m dot. Okay, you might have seen it expressed that way before. Okay, so we have our power here, and we can rewrite some of these variables in terms of things we actually know. So first off, let's talk about velocity. Okay, so velocity is related to flow rate, right, and the area. Q equals V times A. So V equals Q over A. A is just simply for a cylindrical pipe, which is usually what we're talking about in this situation, is just pi d squared over 4, right? So we get pi d squared over 4. Okay. And now what's Q? So Q is volumetric flow rate, right? And we're interested, actually, we have other things in terms of mass flow. So mass per unit time is going to equal the density of a fluid times its volumetric flow rate, and that makes sense, right? So what we can do is plug in for Q here, M over rho. Right? So now we get 4m over rho pi d squared. Okay. Now we can take this right here and plug this back into our expression for power. Okay, so we get 4f L over d. Then we have, I'm going to try and do this all at once here. So we have 4 squared is 16. Then we've got our mass squared there. Okay. Divided by our 2. And then we have rho squared, pi squared, and then d squared squared, which is d to the 4th. Right. Times, can't forget this guy, drop it down there. Okay. Let's go ahead and kind of combine these terms. We get 4 times 16 divided by 2 is 32, right? 16 over 2 is 8 times 4 is 32. 32 times F L m dot cubed over d times rho squared pi squared, and oh, I didn't even notice this, but we got 5 d's on the bottom now, so we just say d to the 5th, right? Okay, and that's our expression for power. Now, considering all of these things together, we get the cost is equal to our capital cost times diameter times length plus our power or pump cost times our expression for power, which is this 32 F L m cubed over rho squared pi squared d to the 5th. Okay, now how do we derive an expression for the optimal pipe diameter? Well, if we want to optimize the cost in relation to diameter, we just simply need to take the derivative of it and set it equal to 0. So the derivative cost with respect to diameter is now equal to, actually, I'm going to rewrite this on the line below so that I'm not confusing myself. We just have our capital cost times L for this term, right? Plus, okay, over here, we have d to the negative fifth, right, times this expression. So that will become a negative 6, and then we're going to bring the negative 5 out front. So actually this is a minus. Negative 5 times 32 is 150 plus negative 160. Okay. Times F L m dot cubed over rho squared pi squared d to the negative 6, right? Okay. And this is set equal to 0, right? Because we're optimizing it. And then let's go ahead and solve for d. So we can move this term to this side and then divide by everything but the variable we're solving for. And we get d to the negative 6 equals cc times L, capital cost times L, over 160F L m dot cubed over rho squared pi squared. Okay. And it looks like our L's cancel out, and we can make this look a little cleaner. We get cc times rho squared pi squared over 160 friction factor mass cubed. Okay, and then obviously we want to separate, we want to get rid of this exponent, so we can put this to the power of negative 1/6, negative 1/6, and these cancel out, right? This is just equal to d now. And that's our optimal pipe diameter. Is this, oh, and I almost forgot, I didn't carry this PC down. Excuse me. So 160 PC. Can't forget that there. And that moves down to here and here, right? PC times 160. Okay. And that is our final expression there. Now, this guy right here. So that guy's a little tricky, but if you remember, we already said that this is equal to our, right, derivative mass with respect to time is equal to rho times q. So let's go ahead and bring that out of the equation here. And we're going to get, I'm just going to rewrite this real quick. Okay, and then this mass term cubed to the negative 1/6 is the negative 1/2, right? Negative 1/6 times 3. Yes, negative 1/2. Okay, so this is going to be this, right? And Q is just the velocity times the area, right? And velocity, or an area of a cylindrical pipe is just pi r squared, right? Or pi d squared over 4. So velocity equals, or excuse me, Q equals V times pi d squared over 4. Yeah. Okay. And so we can put this back into here. We get V pi d squared over 4 to negative 1/2. Okay. And that is our expression there for the optimal pipe diameter. Now, what's really unique about this, the reason I had us bring mass out, this flow of mass with respect to time, right, is because when we change this to velocity, we can actually solve this for velocity, because you can see there's d on both sides of the equation here. We end up solving this for velocity. And what's really interesting is even as these capital costs and pump costs change with the market over time, the optimal velocity will pretty much always stay about 2 meters per second. This is interesting, and it actually works because the capital costs increase and the pump costs increase. When they increase from the market and fluctuate, they increase proportional to one another. So when the capital cost increases by some amount, the pump cost usually increases by about the same amount, or vice versa when they decrease, right? And so this constant really just stays about the same, that CC over PC value. And so, yeah, that optimal velocity, if you solve for it, is pretty much always around 2 meters per second. Okay, I think that's all we need to do for this problem today. I don't feel the need to go any further. We'll join you next time for, well, I guess just some more problems like this. So thanks for watching, thanks for pulling through with me, and see you next time. Thanks.